Okay, yeah, so the recording has started. Thank you so much, all of you, for joining. Thank you so much, Dr. Erin Buchanan, for agreeing to this workshop. We are very grateful to have you. Before I introduce our speaker today, I'll quickly introduce myself. Hi, everyone. I'm Pooja Kulkarni. I'm the founder and director of Psych rstats Club. Psych rstats Club works towards making statistics in R more accessible and today's workshop is made possible by the grant and aid received from Society for the Improvement of Psychological Science. And this grant has made it possible for us to make our resources across various skill levels accessible. We have also partnered with ABRIR to make the translations across different languages accessible around the world. And today we are very thrilled to be joined by Dr. Erin Buchanan. Dr. Erin Buchanan is a professor of cognitive analytics at Harrisburg University in Pennsylvania. Her interests include computational linguistics as well as improving statistical practices. She is the creator of the famous YouTube channel Statistics of Doom, which has amazing tutorials on R and statistics. She has taught many statistics courses, and several of them are also available on DataCamp. She has uploaded many tutorials for free on YouTube and her websites, making many of these complex topics more easily accessible. And we are very grateful to have her as the speaker today. So, yeah, without further ado, I would invite Dr. Buchanan to take the floor.
Perfect. All right, so let me share my screen, and thank you for the wonderful introduction. I'll try to keep an eye on the chat as well, although it is harder to do in Teams sometimes.
I will let you know in case there are any questions which require like immediate answers. And uh, also, everyone, please know that there will be some time towards the end for Q&A. So you can raise your hand and we will unmute you and you can speak then, or you can keep putting your questions in chat. We can take them towards the end during the Q&A. I hope that's fine.
No, that's perfect. I just trying to get everything on the right screen here. So someone asked about the slides. You should be able to see everything linked here in GitHub. There's nothing in the OSF storage, but you can download it the same way. So if you click on the top, just on GitHub and click download a zip, that'll download the whole set of files for you. So you have all the pictures and all the data, including the markdown files. If you just want to watch with the slides, there is a static link. I also put it in the chat that has this hosted on Quarto that has exactly what I'm about to show you. So just kind of FYI on where everything's at. And then I will get started. Perfect. Well, like I said a couple minutes ago, good morning, good afternoon, and good evening. I am so thrilled to be here today. I'm very honored to be invited as well, because I consider myself like an MLM junkie, but I don't know who would be like the expert. So I stole some slides from the experts, and I'm hoping that we can kind of get into MLMs today. So main goals for today's session include understanding what types of data are appropriate for multi-level models. So you may think, I assume if you sign up for a lecture on a Sunday, you're interested in them, but you may not think, oh, I don't have any data that's like that. And my running joke in our research lab is that everything is a multi-level model if you try hard enough. So we're going to try. And then we'll review some basic equations and terminology. I think if you're like, oh gosh, math, that's okay. You don't have to get that part. But it is helpful to hear some of the very confusing terminology in MLM that took me kind of a long time to sort through in my brain, and I still find it somewhat confusing. So I'm just hoping I can kind of clarify when you see these level 1, level 2 kinds of discussions, what people are talking about. And then how do we implement those in R? So I have 2 different examples, one from cognitive science, which is my area. That's more of a sort of vanilla MLM. It's this, I guess, the simpler version. And then one from clinical science, where I work with a bunch of friends who do research using daily diaries. and how they implement this level 1, level 2 differently than the way we describe it in cognitive. So I kind of tried to pick 2 examples that showcase the different ways that people discuss MLM in the literature and psych. So quick terminology note, you'll hear multi-level model, which I kind of like using MLM because it has that association with multi-level marketing schemes, because effectively they're the same idea, the structured data. We have one person underneath other people, underneath other people. That's the type of the way the MLMs in math work. But you'll also see people who call them random effects models, mixed models, which is kind of confusing because repeated measures ANOVA, sometimes called mixed models when you have both between subjects and repeated measures, random coefficient models, hierarchical models, which is the first way I learned them. I think that name is left over from very famous software called HLM. That's still great, but all of those are the same thing. Okay, all the same type of math. So if you see somebody say they did a hierarchical model and then they start talking about random coefficients, you know that, okay, we're doing the same type of thing. Okay. So I'll start with non-hierarchical data. This is the data that most of us have, right? So it's often thought of as like between subjects data, where each person has one measured time point or one measured outcome. And in the data set, each person is with one row of data. Sometimes this is called wide data in the traditional tidyverse typology, where each column represents one variable. Okay. And so this is where, you might do a regular regression with this sort of stuff, where you have a dependent variable and 6 predictors, but none of those are measured multiple times. Okay, they're not the same variable measured twice, or the same concept measured across time, for etc. That's traditional regression. Hierarchical data, right, is where the data contains some form of structure, where those data points are nested. So I'm trying to really highlight here some of the words that you'll see. So nesting and clustering are really popular words. They effectively mean the same thing as well within that variable. Now, the data might actually be between subjects, but you don't realize that it's hierarchical. And so I'm going to provide a bunch of examples here. So let's say we have I'm doing a study right now, where I'm actually studying if students are any good at predicting their own learning. Traditional judgments of learning, the sort of Dunning-Kruger thing, but I have multiple exams. So they predict how well they think they're going to perform on the exam. So each person is tested multiple times because we have 2 exams. Okay, that would be hierarchical data, where the nested part is the fact that there are multiple exams. We might have prices of healthcare equipment over the last year. So that's the same equipment measured over time. So if you look at inflation or any kind of thing where you're measuring it over time, if you say the word time, it's probably hierarchical data. And then an unexpected example. So happiness scores for individuals. So far, it sounds like between subjects in multiple countries. So if you want to control for or examine the effect of country or geopolitical region, as we like to say, that becomes a nested variable because you have multiple measurements of that country. So you have multiple individuals. So it's like you have several between subject samples. And you can treat that in a hierarchical way. So in theory, what used to happen and what still happens in many research labs is that we take all of those measurements and we create one average score for each of those multiple times. So for example, we could take that group of students' exam score and average it so that you have one exam for each student, and then be whatever the next measurement is that you're interested in, right? Is class 1 different from class 2, for example? Each exam also could have an overall average. So there's actually 2 ways to average this one. Okay. For that healthcare equipment, that price over time, we could take the average yearly price for each equipment piece to calculate. And for our happiness scores, we could create one score for each country. And that mathematically does reduce the complexity of the data. But that's lame. So what we should do is continue to use all of that data as interesting pieces of information. So when we create these averages and we sort of reduce the complexity, it does allow us to use simpler models, but it also reduces the power. Okay, I have a little bit on power at the end. I didn't want to go on forever because I probably could. I love MLMs. But one advantage of them is that they have more power because you're using every data point instead of averaging data points. It ignores that measurement error of the multiple data points. So it sort of assumes that all of those are measured the same well, right? And that everyone is the same. And so if you're familiar with item response theory, it's that idea that a very popular model used to be to assume that they all had the same sort of effect, which is silly. We all know better, right? So not every item in a study has the same impact or the same effect size. Not every person in a class has the same skills. So we shouldn't ignore that error or average over it. Instead, we should treat it as part of the equation. It may hide some interesting relationships that exist in the data when you actually use the individual data points. So you can kind of figure out maybe where the heteroscedasticity might be coming from. So when you have that variance of some people do better than others, it might be simply due to the sort of participantness is the way I like to think about this, but the individual differences in the data. And I can account for that rather than pretending like it's something I don't understand. All right, this is where MLMs come in. Okay. So multi-level models allow you to retain that power because you analyze each data point while controlling for the non-independence. So that's the real problem here. One of the assumptions of regression is that each point is, I think it's called IID, independent, and I could never remember. Distributed, don't remember. But the idea is that they are all independent observations, identically distributed. Okay. And so that means that my data has nothing to do with your data. Okay. And my example that I remember from my stats class, let's not talk about how many years ago, is that if you were taking people's weight on a scale, right, and it was raining really hard outside, and there was mud on the scale from where your shoes left the dirt, then the next person's weight is no longer an independent measurement because you came first and tracked mud everywhere. So each person's weight is now affected by the person before them. Sometimes that's an interesting research question, but it does violate the assumption of independence. And so anytime you have multiple measurements of something, okay, your data is no longer independent. So in theory, data is never really independent, right? Because of culture and language. But we like to pretend for most cases. But if you have that variable that you know creates the non-independence, or at least you think it does, you can control for it using a multi-level model. Excuse me. So heteroscedasticity, or if it's too early or late in the evening, is this idea that across all of the measurements, we have different variances. So across the values of X, the variance for Y is not equal. And we'd want homoscedasticity, but honestly, when I teach repeated measures to students, I always talk about how it's almost impossible to get homoscedasticity, or in traditional ANOVA, sometimes you talk about Mockley's test, right? Like that thing never works out because often part of the research design is to change that amount of variance. So if you're doing like a smoking cessation study where you're trying to get people to quit, the variance naturally cannot be the same, or you have totally failed at your job, right? So you assume a lot of variance at the beginning. Some people smoke a lot, some people smoke a little. Ultimate goals, no more smoking, right? No variance. So you can't win. But by using these types of designs, instead of averaging, we can now maybe investigate why the heteroscedasticity is there. Okay? And it might simply be participants. And that's often Part of the issue is individual differences within people, and now I have a way to point to that, excuse me, rather than just kind of hand waving and hoping it goes away. Another benefit to the design to using these mathematical models is that you can have missing data and it's not a big deal. Right? So if I had 4 exams and a student missed an exam, but I didn't really want to measure that as a 0, because technically it's a 0, I could just sort of exclude that. But then, like a NOVA type design, I would just lose that entire participant because they didn't have complete data. But in these types of designs, you just kind of gets like, oh, okay, cool, and you keep going. So you can have missing data, but still use the other data points from the same participant ID or data point ID. And so missing data becomes less of a problem. It's still a problem. You gotta know why, but it's not as big of a deal. So if equipment prices are missing from May, you could still model the data even without those numbers. And last, it allows us to control for measurement error due to the study design or the measurement tools themselves. A lot of times I do these just simply to say, hey, we have participants tested 100 times. We're controlling for that error. We don't care about the rest of it. Moving on. Sometimes it doesn't even help a model. So I have had models where we controlled for participants and it didn't do the model any good. Some people were like, oh, you should take it out. I was like, whoa. I don't want to violate the assumption of independence, but also I wanted to note that it didn't really matter. So I do say, like, at least make sure you're not violating the assumptions of regression, but you can also see how much it matters. So we'll look at effect sizes today. The effect size is actually based on the fixed effects, so the question you're interested in usually, and the random effects. So you can kind of look at how much the variability is between data points and participants. There's also a way to calculate ICCs, interclass correlation coefficients. I like abbreviations today are jumping out of my brain, but ICCs also kind of measure that like a participant variability. All right. We'll do the people's least favorite part first. So if I look at a traditional regression equation, so this is simple linear regression. Let's assume ordinary least squares. This is the general math made for regression with one predictor. So let me talk about each one of these little pieces one at a time, and then we'll show you how MLM is not actually anything fancy. It's just regressions with regression. So y hat sub I here is the predicted dependent variable score for participant I. So it might be your exam score on average. It's got the little hat because it means that it's predicted. That's important in a minute. B0, generally considered the y-intercept. And the intercept is the average score for y when x is 0. Okay, x being 0 might not make sense. So if you're using traditional Likert scales, right, with 1 to 7, x is actually never 0. But mathematically, this is the y-intercept if x could be 0. So it's important to remember, it's not just the average score, it's the average score if x could be 0. Because what is our best guess for someone's prediction? Like if I think about this theoretically, and I'm trying to guess what next month's equipment prices will be, for example, the best guess is the average. Because that's the point of the average, right? It's right in the middle. It's where most of the data is. Okay, another good guess might be the median. But if we're going to use traditional normally distributed data, the median and the average are approximately the same. Okay, so our best guess is the mean. And then from there, we can add predictors to help us make our guess better. So B sub 1, 2, 3, 4, whatever, are the slopes for the individual predictors. So how much weight does that predictor have when predicting y? Or very traditionally, for every 1 unit increase in x, we get b unit increases in y. So as one goes up, the other goes up, or they both go down together, or one up, one down. And so that tells me kind of a weight, but B, and I very purposely did not standardize these. If you look up equations, Google this and end up on Wikipedia, you'll see people list them as beta, but I find that a little confusing because this is not a standardized equation. I think it's just the traditional way to do it. So I'm listing these as B to make it clear they're unstandardized. So B here, if we convert it into beta, becomes more of an effect size. X sub I is our score on our first predictor for each participant. Okay, that might be months in our equipment data. As we have all seen, prices increase over time. For my student exam example, that could be previous achievement, right? Best predictor of future behaviors, past behaviors. So their previous scores on exams could predict the next exam. And then happiness levels by country. Oh, that one's a little harder. It could be median income. And the last but not least, we never get anybody exactly right. Okay. So this little E out here is for the error or the residual. Okay. And this is the stuff that you look at and make sure it's not all weird when you're doing checks for homoscedasticity or linearity. But what it is their actual score, so the score in the data, minus their predicted score. And so generalized least squares or ordinary least squares, because we're going to look at generalized least squares here in a second. What they do is they try to minimize the error. So what is the equation that best minimizes the error? Because it's called least squared error. And what that does is it allows us to get the equation that best predicts as many of the data points as possible. Some people's scores will be really wrong. Some people's scores will be perfectly right. But what's the equation that minimizes these best? Now, the nice thing about linear regression, this equation, is that it's called a closed form solution, which is a fancy phrase of saying that there is a mathematical way to plug and chug and get the equation that minimizes the error. As taught through matrix algebra, which I will not make you suffer through this morning, afternoon, or evening, because that's what computers are for. But multi-level models actually are generally mathed with maximum likelihood estimation or restricted. What does the E stand for? RIML. I have it in my head as RIML. Apparently acronyms are not going to be my jam this morning. But the other version is RIML or restricted expectation, I think. I don't remember what the E is, but a different form of maximum likelihood. And anytime you hear maximum likelihood, it generally means that there's actually not one right answer. It's an iterative process to find the right answer. So it takes this equation and it sort of iterates through the next couple of slides I'm going to show you to find the best answer. All right, now we're getting into terminology. So it's still regression. I'm going to show you linear because it's the easiest place to start and the best place to find tutorials. But you can also do this with logistic regression. You could do Poisson, or that we can actually apply this to structural equation models. I've done a couple of those. It's not that much fun. Or any type of regression. I think you can even do them with GAMs, the general additive models. So it's still, it's just a way to structure the equations. And so we can still use, different types of distributions underneath the hood. But we'll stick with the normal model. And so when we walk through these in a few minutes, I'm going to use the same system that I teach my students, which is what's going on with the overall model, right? Is the overall model better than nothing, right? If not, then time to scrap it and start over. But if the overall model can at least predict somewhat, then which predictors are the best? So you might have a model that actually just has random coefficients, and you can show like how much variance is accounted for, and it's the interclass coefficient. So I got one of my acronyms back, but not the E for RIML. So, okay, that sounds great. So you haven't told me how this is different, right, than linear regression. This is the part where it gets different. Okay, is its random effect structure. Okay, so we're going to take that equation we just saw and add layers to it. So fixed coefficients are the things that you're used to working with, things like intercepts and slopes. So anytime there's a little b, that's considered a fixed coefficient in our traditional system. And that's where, assuming that the intercept is the same for every person, the slope is the same for every country, for example, or the change in equipment price, from my other example, is the same across time for every piece of equipment. Once you say that out loud, I feel like if you've ever played with data, that should feel silly. Right? Because, I mean, even the simplest example that there are different types of students, right? Not every student is an A student. And so we have, clearly we're going to have different levels of starting points, much like today. I tried to shoot the middle here of terminology and skill sets, where some people might be fairly new to R, and this might be a frightening lecture, and some people might be like, I've done a couple of these, but I want to hear what else she has to say, and you're probably half asleep, right? So we know that there's this variability. And so modeling this as if everyone has the same numbers, we'll start to feel like, oh, that's probably not a good idea. How do I fix that? Well, you add random coefficients. Okay, and the way that this being called random, I understand why, but like it's bad terminology because they're not really random. What they are is variable coefficients. Okay, that would be a better term for them, where they're allowed to be different across those different contexts. Okay, so it can be different for each student, different for each piece of equipment, and different for each country. And what happens is you get a model with the fixed coefficients, and then you find out how much that varies. And so if the variability in that coefficient is low, that implies that, oh, it's approximately equal across all these different contexts. The variability is high, that's a really interesting result that maybe some of our replication crisis, obviously it has a lot of different influencing factors, but some of that might be the fact that we've been modeling all of our data as if none of these things vary. And it could be that we have a lot of variability, and sometimes people only took variability from up here, so it worked out. Other times people took variability from the whole range of possible options, and it was a null result. Right? That's a potential place that things have been going wrong. But let me explain what random coefficients really mean. And I only use the term random because that's what you'll see. I really don't love it. It's sometimes called a grouping variable, a nesting variable, or a clustering variable. And you base this on the structure of the data. So where's the non-independence, right? So how would I group people together? Sometimes I don't love calling them grouping variables either, because that kind of implies that there are these like distinct groups. You can have random coefficients that are not between subjects. Okay, time could be a random coefficient, where it's not time 1, time 2, time 3. I actually have that example here in a little bit. But it's the variable that is clustered in the data. And usually that's participants, since I'm talking to psychology people. That's normally the participants in our data set, but it doesn't have to be. I've been trying to provide different examples. And so you keep using my same examples. The students potentially could be the random variable here. We could also use exam or both. And then if you had instructors, like if you had multiple classes, you could also use that. So you've got kind of 3 different levels to the variable. The healthcare equipment is probably the equipment, but it could also be time, depending on what you're trying to do. And then our happiness scores for people in multiple countries, that one is going to be country, unless you measure people multiple times. So it isn't necessarily like set that it will always be participant. Right? It kind of depends on how your data is structured. So if you ever do any work where you measure things across multiple sites, like I think like clinical people might do, then that might be a variable you want to control. So this level 1, level 2 thing, I find this to be the hardest entry point. It's like, you're like, okay, cool, this is just regression on, regression on regression, neat. And then somebody's like, well, is it level 1 or level 2? And you're like, what are you talking about? what is it about statistics? This is just an aside, but what is about statistics where the terminology is so terrible? Type 1, that doesn't mean anything, right? Type 2. So let me try to clarify level 1, level 2 with an example, because I find that works best for me. Okay. And so let's say we're trying to predict someone's language test score. So we're doing education research, and we're trying to predict the test scores for, English, for example. And we're trying to disprove that myth that women are better at language, right? So we'll take the gender of the student, and then we'll add in what type of school it is, right? Is it a private school? Is it a public school? Is it one of those cool magnet schools? So here in the States, they have these schools that are sort of targeted at specific types of, like a math magnet school would be more heavily into STEM, right? And then they have art schools where they're doing more STEAM, I guess, is the new terminology. Right, so we've got the gender of the student and the school type. So this is a good example for level 1, level 2. Okay, so our dependent variable is the test score, and we have test scores for all of our students who happen to be in these different types of schools. So hopefully you can see that the data is structured such that we have schools and then we have students. The independent variables here are the gender of the student and the school type. And the clustering variable is the school number itself. So this is just literally which school is it. So we actually have multiple schools within that school type. We're not clustering on the school type, we're clustering on the school itself. So there might be something weird about this one school. Let's say they're in a really, and I'm using the United States as my sort of frame of reference here, but if you're in an area where the median income is really high, you're going to have more resources than if you're in an area of the world where the median income is low. So you got to control for that difference by just, using the school number. So some of these schools might just have lower test scores, not due to students, but due to resources. And so neither of our two independent variables are nested variables. Okay, we can actually use them as nested variables. Show you that example in a little while. So okay, that's our structure. This is how we'd write our equation. What makes it level 1? Well, level 1 variables are at the level of the dependent variable, so to speak. So each test score is tied to one gender. So I kind of think about level 1 as if I have a different number for each row in the data, or I'm supposed to anyway, right? So each test score is tied to a specific individual who has, a specific gender in this example, and each row represents a different measurement of that person. And so that's a level 1 variable. I have variability in my independent variable based on tied to the dependent variable. Okay, that's normal data. Level 2 is where it gets different. So level 2 is where I have the variable is repeated across independent observations. So if I think about each person being a row, right, where we have their test score and their gender, and that's different from row 2, which is test score and gender, blah, blah, blah. But the first 4 rows might have the same school type because they are all in the same school. Okay, that's a level 2 variable, meaning that there's no variation in the data predicting the dependent variable because that's part of the cluster. So level 1, you can kind of think there's some great other great tutorials online, but I think examples help me. So level 1 is where I have variation for each of the dependent variables. Okay. Level 2 is where I don't. The numbers should all be the same because it's a variable above the first level. Okay. There are clusters in this group. Hopefully that helps. I find this terminology to be the worst part about this. Running, it's actually easier than remembering which one is level 2, 1 and 2. All right, same equation. Okay, this is a level 1 equation. And so if we check out this equation is actually the same as the regression equation. Boop. Okay. Same equation. We just added some j's to it. Same equation. And so that's really what I want to highlight, is that it's not that different. We're just controlling for the structure in the data. So the J is in the new part, and I want to walk through level 1 equation and then a level 2 equation. Okay. So the Y hat here is the predicted score for the dependent variable for the participant who's in level 2J. Okay. So whatever their level 2J thing is. Okay, it might be the math magnet school. In our time example, it might be measurement time number 1, right? So whatever that level 2J is. Okay, it's their predicted score at that, for participant 1 at that level 2J. The B0 is still the intercept, but now because we have these clusters, it could be the intercept for, cluster J or cluster J, J2, J3. So if I go back to our school types, it could be the intercept for school number 1, school number 2, school number 3. So if I don't use any clustering variable, we create an average and it becomes a simple linear regression. Okay. If I do use the clustering variables, and now I have a different intercept potentially for each of those J clusters, okay, which might be school 1, school 2, etc. B1 is still the slope for our level 1 predictor, but we could potentially have different slopes if we used random effects. Xij is still the level 1 predictor for participant I, who is in this level 2J. And we still have our error. So all we've really done is basically said, well, okay, all of our gender predicting language scores, for example, sometimes they're in the math, math magnet school, sometimes they're in this other type of school. And so we could essentially have a little equation for each school. But we don't really want that. We want an equation that, well, I mean, you could do that. A lot of people do. They just separate them out and then compare the coefficients. It's one way to do it. But if I want to put it all in the same model, I have to add that level 2. So that's what this next part is. Okay. So depending on what type of random effect structure you pick, so you'll see differences in these equations if you look these up. I'm going to recommend an online free book that is partially written by Jess Flake and one other person that shows you when you would use all of these. But let's pretend like the most complicated thing is happening. You're using all the random effects that you could possibly want. Okay, this would be the structure. And so we've got to calculate the slopes, I'm sorry, the intercept and the slopes separately. Let me back up. So we've got our two possible places that we could have random effects, okay, a random intercept or a random coefficient, if we want. If you don't want, it just gets all averaged down. But if you want, now I have to figure out how to calculate this, because if I have a level 2 variable, I now have the ability of that information to impact it. So here's what happens. We get the level 2 predictor, which in our case, in our example here, is school type. The intercept, this is the grand mean of the dependent variable here. So the overall intercept, that's this thing, is the grand mean, which is what it was before, plus the effect of that level 2 predictor on the intercept for the participants. So how much does the school type push up or down the students' scores, right? So if you're at a school, like an art school, maybe that really pushes the language scores up. So you're going to take that grand mean plus some extra bonus for being at a school that really focuses on the creative writing, for example. If you're at a school that maybe is focusing on engineering, engineers don't need to know how to spell. This is a joke. It might push your scores down. So what you're doing is you're changing the intercept based on that level 2 variable. But since the level 2 variable doesn't vary by student, it varies by sort of group, we calculate it at the higher level. Okay, it impacts the whole group in the same way. So it's either pushing their scores up or pushing their scores down. And then the U here, again, we never get anything perfectly right. It's just a different form of error. So how different is this thing from the overall intercept, which at this point becomes an error term? Same thing with the slopes. Okay, the y10, these terms, they're just so unhelpful, right? This here is the average slope. So if I think about how do I estimate the slope? Well, it's the average slope plus how much the effect of level 2 impacts my slope now. So maybe it's that I'm at this arts focused school and the instructors are really aware of the fact that there's this social feeling that girls are better at language. And so they try to neutralize that. They try their best to keep it out. So maybe that effect is that it neutralizes the differences that are in other schools. And so it pushes that slope to 0. So it actually brings it back down. But at another school, they don't think about this social embedded stuff that we have, and they just treat everyone like normal, which means they have these implicit associations. And so it really pushes girls' scores up, for example. So the impact for one group might be to neutralize the slope, so it kind of brings it back down, and the other group's slope might bring it back up. So we're seeing how different these are. If you've ever done a simple slopes analysis with like an interaction, same feel, but it all like kind of builds in. So it measures how much it impacts the overall slope based on what those group differences are. And it's not always groups. I'm using the word group here because we have like, math magnet school versus art school in my example I've made up. It might be a continuous variable, so that's a little harder to talk about, but like how much that variable influences the impact. And then again, we have an error. It's got a different letter because it's at a different level. So I'm just wanting to highlight really like, if all of that was sort of like, okay, sure, Erin, that's okay. The basic gist is that the level 1 equation is approximately the same thing. Right? We're still using the idea of least squares. We still get an intercept. We still get a coefficient. But once we start adding this random structure and the level 2 effects, we're really kind of mitigating the global effects of the clustered part of the data. Okay, not mitigating, we're estimating that effect. Now let's get into random coefficients just a little bit more, and then I'll show you some examples. So that random intercept, I've been talking about it this whole time. And I went back and forth on which way to order to do these slides, but I thought we would get the math out of the way. But it allows each random cluster to have a different intercept. So each school can have a different intercept in our example, right? And then we can use the sort of impact of school type to examine the changes in the slope. And this is really handy. The most common thing that you'll see people do is random intercepts, because it really allows you to control for the sort of unwanted variability that exists due to people, or, I'm measuring this at different places, and, this one place has a nicer building than the other place. Now, remember that intercept is our average score for y if all of the x's are 0, but now it's sort of the average, it's the average score still, but I can see how much that average varies based on my cluster. Whereas before, this was all error and you didn't know what to do with it. So really, we're taking the error term and we're just saying, well, it's partially because of this variability. So it's effectively the average for each cluster separately. Okay, sometimes clusters are people, and then sometimes clusters are schools in our example. Now, what you'll see in the R output, if you ever dig into the random effects estimation, it looks weird because you're sort of expecting it to be like the average score for each person, but what it actually shows you is how much they deviate from average. So let's say our language test score average is 57, making up a random number here. If another school has a 59, it'll show you 2 because it's the deviations from average. So you don't actually see their score. You can calculate it by taking the intercept plus their score. But that, if we remember, is here's why, right? We've got our average plus the effect of that cluster. All right. So if you're ever looking at those, expect them to be a little odd because they'll show you how much higher or lower they are from average. It's the deviation. First time I looked at it, I was like, what's going on? The scores are in the thousands and these are 2 points. So that's what it is. Now, a random intercept, this is stolen from the Andy field, can look like this. So the dashed line here is the overall linear regression, which is not really a great representation of the data. But if we allow each of the colored dots to have their own intercept, we get a much better picture of the data because it's made up data. And what you see is they have very different intercepts with actually very similar slopes. And so it just allows each one to best estimate only their points, and then you kind of get an overall equation. Now, random slopes, the other place that you can add stuff, and it allows each of those random cluster variables to have a different slope. I find it harder to explain random slopes to people, but I have used them every once in a while in analyses. I think that if you were to pick which one people use the most, it's definitely random intercepts. So you could do just one random slope or many of them. Don't recommend, but you can. And what it does is it creates a different slope for each of our clusters. And again, if you look at the output, it shows you the difference from the overall slope, the fixed effect slope. And here's an example of just random slopes. Okay, they all have the same intercept to this point right here, but different slopes. And that would better capture the data. You know, if you looked at this data with the linear model, you would probably not see anything. You would think that nothing was going on. In reality, what it is the very traditional interaction effect, where one group has a really strong slope and one group is kind of flat, and the other one is a negative slope. And you would miss that if you created averages. I would say this scenario is a little unusual to just do a random slope. Mostly people do something like this, where they have random intercepts and random slopes. Now, it may be that the slopes don't vary. It may be that the intercepts don't vary, but by having it in the equation, you allow them to. They don't have to, but they could. So you don't really lose a whole lot of power by allowing them to. However, it does increase model complexity in the sense that it may take a long time to calculate if you have a lot of individual clusters. So if you have 15,000 participants and you want each one to have a different slope, that takes a long time to calculate. That's the only real disadvantage. So which one should you use? Random slopes, random intercepts, which one? Models are generally built from simplest to most complex. This is sort of how everyone's taught with linear regression as well, right? You start with, especially in hierarchical regular regression, where you add predictors as you go. So we'll start with our null or intercept only model where there's no predictors in the equation, which is effectively saying what's the average score. Then we might add the random intercepts, then add the fixed effects. Okay, fixed effects are predictors that we don't expect them to vary. We're not going to allow them to do anything, give you one score. And then maybe adding some random slopes. And I remember I was using some of these notes for a class, and my friend reminded me that her MLM teacher said, no, you should really do most complex and whittle it down to the simplest model. So some people do like to do it the other way. What's the most complex model and then reduce? I think it's easier to start with simple and get more complex, but either way, you can go in either direction. There's no, these are those camps that just have feelings about which way to do it. And how we compare models is going to be with the AIC, or the Kaki Information Criterion. That one I can remember. And what you do is you pick the model with the lowest AIC, okay? Even negative. It's not the closest to 0. I remind myself of this every year. I'm like, which one is it? It's the one that is literally the mathematical lowest. So if it's -2 and -4 is better. Okay, you feel like we want this to be closest to 0 because of the way that we tend to treat, error terms. We want them to be 0. In this case, we want the smallest. A number, an AIC all by itself doesn't mean anything. It's only useful in comparison. All right, now the fun part. So I have all the packages. One of the cool things about doing this in Quarto is it does allow you to copy and paste. And so you can just kind of copy if you ever use the slides. If you're opening it up, it looks like a regular Markdown. It runs like a regular Markdown. It just happens to be Quarto. So a little bit on the packages we're going to use. I love Rio so much. It is magical. It's a data import library that will mostly handle whatever weird data structure is going on for you. It's magical. Okay. In LME, I like a lot better than LME 4. At this point in the rstats competition, they're pretty much the same. So NLME stands for nonlinear mixed effects. It will do linear as well. LME4 is really popular. There's no reason to pick one or the other, honestly, at this point. They used to have fights. Now it's just preference. So I'll use NLME, but people love LME4. Okay. And it's LME4. I got excited here. dplyr, because dplyr is awesome. And then I'm going to show you some stuff from EasyStats. EasyStats is like the tidyverse of stats. And my friend was like, why aren't you using parameters? I was like, what? It is such a cool package. It's a whole host of packages that allow you to do some really easy data checks and manipulate and write out reports without thinking. That's a good and bad thing. The C library is also part of EasyStats that helps if you want to take some of these pictures. They turn out to be ggplots. Very cool. And you can edit them. But performance parameters and report are the one I'm going to use. And then MUMIN is a package that does multi-level model effect sizes. There's kind of a contention about effect sizes in multi-level models right now. This is an area that I would say is sort of not decided. There are a couple of new papers out in behavior research methods that are looking at effect sizes for individual coefficients, sort of like PR squared or SR squared in regression is pretty popular. And people are still arguing about them. So for me, the jury's out, but MUIN is really great for an overall picture of the effect size. And I wish I could make the font on the coding a little bit bigger, but I don't think I can. Apologies. All right. So I'm a cognitive psychologist. I pretend to be a statistician on the side. And so a lot of psychology projects use repeated measures data. Yeah. And so this is from a data that I've been building. It's resubmitted, fingers crossed, that it'll get accepted, where it's a large-scale semantic priming study. It's called the SPAML for fun, some semantic priming across many languages, and I have the link to the preprint here. And priming, if you aren't familiar, is the effect. It's a very strong effect where if I show you a pair of words that are related, cat, dog, you're much faster at processing something like dog than if I show you a pair of words that are unrelated, like spoon, dog. Okay. So if we compare those two instances of dog, you're faster in the cat scenario than in the spoon scenario. And I was giving a workshop this summer on multiverse analysis. So I have this data kind of prepared. So I thought I'd use it again. But these are the priming trials in Serbian, okay, an under-resourced language where we don't see as much cool research on. And so I'm really happy to say that we have data in a bunch of languages, but especially some of these languages that you don't see as often. And the data is all available. So if you're interested in way too many priming trials, it is open source. So the dependent variable in our example today is going to be response latencies. So how fast can they whack the keyboard to say, yes, this is a word. No, it's not a word. The independent variable is a level 1 variable, meaning which condition. So for each response latency, it's in a potentially a different condition. Okay? So that is tied at that lowest level. Okay. Now, there are a whole bunch of measurements of the different conditions, right? So we've got unrelated conditions, the spoon dog, and related conditions, cat dog. But the number for the dependent variable is different for each one. Well, okay, sorry, but even though it's related and unrelated, they're at the level of the first one, because in theory, each one is a different measurement, right? They're different words. Okay. A level 2 variable might be something like how long the words are, right? So some of those would be repeated. So I don't have a level 2 variable at all, actually. So you don't have to have them. Now, the clustering variables for this example are going to be participant. So every participant has this innate ability to whack the keyboard at different speeds. Some people are faster than others, just naturally. So we have to control for that facet. Okay, that's not what we did. We didn't do it this way in the paper. You'll see a different analysis. But for example, here, I want to show you like how much it varies. Okay. And what trial. So some words are better primers than others. So if we control for the words themselves, so this, this trial, cat dog is a very strong one, on off, very strong one, but pyramid structure, not a very good pair. So we can control for those inherent differences as well. And this, I would say, in a like psycholinguistic study would be a very common structure. So controlling for the people, controlling for the words. Tiny font. But so what did I do? I imported the data here, right? And then I just took out a bunch of crap in the data set. So there we've got the observation, that is the participant code, right? The target duration is our response latency. The word combo is the individual trial of the data. So it's the prime and the target. Whether or not we should keep those participants and trials. So we had some exclusion rules about people who just whacked the keyboard for fun, right? So we eliminated people who just like sat there and like hit the keyboard to get done, because it's very boring. Priming studies, super boring. So I understand. And then our type here, which is our condition, right, between subjects. Conditions, so words are either related or unrelated. Well, it's not between subjects. It's repeated. But the word itself, is this pair related or unrelated? And I just use some magic of dplyr to eliminate all the trials that don't work, and I'm showing you the data set here. Okay, pretty simple. So I have in this data set 681 participants, so there's going to be 681 clusters. And if we use a random intercept, 681 random participant intercepts. So I can get a really good feel for how much variability there is in people's ability to just hit the key, just like literally hit the keyboards, ignoring what condition they're in. Okay, this doesn't affect the intercept part. It completely ignores the actual question I want to know, as if the related pairs are faster than the unrelated pairs, right? This is the simple look at how fast people can hit the keyboard. I'll also get 2,000 estimates of the items themselves. So if I look at the fact that items are repeated across people, okay, so the participants are doing multiple items, and then the items are across multiple people. So I could say, well, that item, if I look at, the participants who completed this item, it's just really weird. And some word pairs are weird. Some word pairs work great. Now I can see how much of the variance is due to the fact that some items work and some items don't. And I can get more into the like actual question, which is the priming. So hopefully that kind of shows that this, with large data sets, multiple measurements, you can calculate. This might be will take a long time to calculate. Okay, by long I mean like 10 minutes, but like, you know, when you're sitting there waiting for the answer, that could be forever. So they can be slow to estimate because they have to estimate every one of those effects. And then I quickly wanted to show like how many, sort of the clustering nature of this. So how many items does each participant have? So there are about 140 trials for each participant, but there's a ton of missing data because people get bored and they quit, or they miss the question, they get it wrong, or they hit the keyboard too fast, many other ors. So there's plenty of missing data. Not every participant has a full set of trials. No big deal. I don't need it. And so we have about 140 trials. If they were perfect, I want to say it would be 150. Yeah. And so we do have, it's kind of also skewed data on the number of trials, but 140, and then, you know, there's quite a bit of variability. Some people have like 7 and some people have the full set. But that doesn't matter. We can use each cluster separately. So first step, I'm going to work from smallest to largest because it makes the most sense to me. But if you like it the other way, just flip the order of the steps. So for our intercept only model, I'm going to use GLS. GLS is generalized least squares. You can also use LM for this first step. You're not going to use NLME or LME4 because in the intercept only model, there's no random effects. Okay, so a lemur, as people like to call it, which just makes me laugh, or the LME function in NLME will not run if you don't have a random effect. So you got to start somewhere. So this is basic linear modeling, but why I like to use generalized least squares is that it actually will allow me to use the same mathematical estimation so that I know I'm comparing max likelihood to max likelihood. It will reduce down to least square, like, you know, your normal math. So it's not a huge deal. It's just why I'm not using LM here. All right, formula equation. So our target duration, this is response latencies predicted by the intercept. So tilde1 means just give me the intercept. Data method here, I think the default is as restricted expectation. I see it, I still don't remember. Is REML, REML. Okay. No particular preference for either one. I just tend to use max likelihood. Okay. And our NA action here, so what do I do with the NAs? Get rid of them. All right, so let's look at our summary. What it tells me is that the average response latency, ignoring everything else, right? Int participant group, item group, what condition they're in, total average, 725 milliseconds. Okay. So this is measured in milliseconds. And we've eliminated things that are way too slow, like less than 160 milliseconds. If you get that value, you have hit the keyboard faster than you could have seen it. And it can't be greater than 3,000 milliseconds, which is 3 seconds. 725 milliseconds. About normal. It's a little high, I think. Most cognitive processes happen pretty quickly. So, you know, it tells me that that is a very not zero, right? Which, cool. That's not really my question, but I can see the intercept. There's a ton of error here. So let's see if we can take that error and slowly reduce it by adding better predictors. So we got our random intercept model. Okay. So LME versus lemur, what's the difference if you want to use lemur? Okay. In LME4, the random component is added directly to the equation. So you would do something like this. I just wanted to show you the difference if you have feelings about using the other one. And so instead of having the random argument, you add it directly to the equation. That's really the difference. Now, I don't want to get into nested and cross effect structures, so I'm going to try to keep this as kind of simple as possible. But do know that you can sort of nested structures. Oof, hurts my brain. So I always just add them as two separate intercepts, but you'll see on the output here in a second that it actually will sort of like think about how the data is structured. All right, so LME function for linear mixed effects, same equation, okay, really all the same arguments. And this is the part that I added something. Now, should you add them one at a time? Sure, if you want, doesn't hurt. I just like, this is for me, a control question. So I just stuck them both in and ran with it. But this is controlling for participant. Give me one slope per, or I'm sorry, intercept per participant. Okay. And then give me one intercept per word combo per participant. Okay. And that's partially happening because they're not perfectly nested. And what that means is that not every word combination is seen by every participant because they would murder me. There are 2,000 word combinations, right? And participants only see 150 of them. So I don't have a perfectly balanced design. It's a missingness on purpose. If you have perfectly balanced where every participant sees every different combination, it could flip-flop them here. But because of my data structure, notice here that it will say, okay, what are the word combinations? What are the intercepts for each of these different observations? So each participant has like kind of a different combination of word combos to create an average for. All right, so let's see here. What are we getting? Here's the random effects part here at the top. I can't highlight very well. I'm trying. Right. So it says, okay, one random intercept per person. Does it tell you that intercept? No, because you have 700 of them. And actually, it's just going to tell me the standard deviation. So my original intercept, 725, that's still the same intercept. If I were to back up, you would see 725. The grand mean didn't change. But now what I know is that on average, the variance around 725 is 135 milliseconds. That's a pretty good amount. It's not 2 milliseconds. Right? So 100, the main bulk of the data is between, oh gosh, math. Is that 500? Yeah, approximately 500 milliseconds. And if I add that to the top here, 725 plus 35, it's like 860. Okay. So that's a lot of variance. That was all error before. And now I've said, well, I know why it's there. It's this people variable. And so I've been able to move that error from being just a residual to now here's what it is. It's the fact that some people can hit the keyboard really fast and some can't. Okay? Or some people just aren't paying attention. And some people are really focused, whatever it might be. And so there's not really like a p-value here or any, like this is significant. We can talk about if it improves the model. So you do have to think about this. I'm going to echo some Robert Kaling-Jagerman, who is working on the new statistics right now. It's about how does that interpreted within your data. So for me, a variance of 135 milliseconds when priming is normally 20 milliseconds is quite a lot. Okay, that's like 7 times the effect of normal priming. So that's a lot of error that I want to account for. Now I also want to look at the word combinations. So how much do the words themselves matter? And it's still quite a bit. Okay, so you want to look at the intercept. It's going to also tell you an error term here, but the important one here is the intercept. So if we calculate the intercept by those word combinations based on the structure of observations, we get another 140 milliseconds. So if I think about that, priming normally is 20 to 50 milliseconds. This could be why your study isn't working because you're just ignoring all of this error if you kind of average over everything. Now, priming normally still turns out, semantic priming anyway, but now I can tell you that the words themselves have a lot of variability and the people. So then let's get into what's actually happening with priming. So then you get your fixed effects. It's going to be the same table, but your degrees of freedom are going to be pretty wildly different. Let me see. Right. So, GLS didn't even give me degrees of freedom. So just kidding. Oh, here we go. So you can kind of look, we got 95,000. We do lose some degrees of freedom because we had to calculate all these values. Okay? But the good news is because you had so many, you're doing okay. Let's see, we do see more standard error. All right. And then down here, it gives me the number of combinations. So there's 95,000 rows of data, but there's 681 observations with 95,000 combinations of items within people. Now, is that because I put them in this order? No. Okay, it's because of the structure of the data. If you flip that random list, they will appear, they have same output. Okay? There are different ways that you can force it into a different structure, but that's a totally different lecture. So I just like, yep, you knew what you were doing here, so I'm going to let you go with that structure. Now the fun part. Okay, let's add the fixed effects. Okay, I just added it on here. It'll ignore this one. It always gives you the intercepts, so it's not actually necessary, but let's also add type. Okay. So type is unrelated and related. Everything else stayed the same. This stuff will generally stay the same. Not perfect. Notice here that the standard deviation of word combo went down a little bit. But usually the random effects don't change too much by adding the fixed effect. And what we see is that it's 49, almost 50 milliseconds, which is quite high. Serbian's data actually, one of the reasons I picked it was because it shows some of the strongest priming, which is sort of interesting. Okay, so about a 40 millisecond difference between the related word pairs and the unrelated word pairs. Super cool. Loved that I found this because it's non-Latin version of their writing system. Everything else approximately the same. Now on this one, I didn't add a random slope. It doesn't make a whole lot of sense to me to add 95,000 random slopes here or by participants, because the slope would be on related or unrelated, right? So I think participants probably have different slopes, but it didn't add it to this model because when I think about priming, I don't, the answer is, well, of course they do. And so I wasn't interested in estimating it. But in this next example, I will show you how to estimate it. Okay, so I stopped there for this model and the fixed effects. All this is cool. It looks like it's significant, but how do I know that what of any of this was useful? Right? There's no like F statistic for my model. So what you do is you can use compare performance, which is in parameters, I think. It's in one of the easy stats packages. It's pretty nice. It'll give me a nice, cute little table of everything. I don't love this, like, I think it's the probability of which one it likes the best. I can't ever totally figure out what this column is, so I always print them out just for myself as well. So if you do AIC of each model, right, we got 136, and then it goes down to 134. So adding that random intercept improved my model because it moved the residual, the error, from being, I don't know what this is, to a variable that I knew what it was. Adding the fixed effects also improved the model. Okay, so we went from 1343 to 1342. And so, okay, my addition of the predictor also improved my model. So I would take my fixed effects model as my best. I had another thought and I lost it. Gone. So you want to pick the model with the lowest number here. Remember, literally lowest. So if you get negative numbers, literally lowest. But the table here is cool. And if you're publishing in a journal that likes root mean squared error, you can also use this table to print that bad boy out. I have seen that lately where people are kind of moving that way. It's more common in economics. All right, so we picked our fixed effects. It wouldn't be a good Erin lecture without talking about data screening. So what's a quick and dirty way to do data screening? There's actually a cool function called check model, but if you have data sets that are this large, it takes hours to run. So I just am going to show you some quick and dirty code to check. You can also check for outliers. Two very cool functions that also work on almost every type of regression input you can imagine. So like I said, rstats is awesome. But if the data is large, you want to do some quick and dirty magic. You can calculate the residuals. I always z-score them because it makes my life easier to decide if the model is any good. So I can kind of use a rubric that I will tell you in just a second. And then I also scaled the fitted values. So the data is skewed, not terribly surprising. Some people are fast, some people are slow. So I got a little bit of skew in here, but not terrible. So my rubric is it between 2 and 2? And how centered over 0 is it? It's not terrible. A little bit skew. This plot's not super great, right? So a little abnormal, a little unlinear. It's not great. But again, between 2 and 2 are the dots close to the line. And if some of you mentioned the YouTube channel, if you've ever heard me like be nice to the plot, so I always tell people this is pretty close. So you want the dots on that line. Some people use this for normality. I use this for linearity. Works about the same. This bad boy though, whew. In a perfect world for homoscedasticity, the dots would be like kind of very random, nice uniform between 2 and 2. As you can see, that is not the case here. Some of that variance is due to people. So it's not like the problem goes away. So I've controlled for it. So some of this is due to people. Some of this is due to the restriction of range in the data. So we cut off the ends, right? The data's got like a hard stop. That's part of it. And then there are other influencing factors like word length, word frequency, kinds of other effects. So it is heteroscedastic, clearly. It makes this like very interesting shape. But there are probably reasons that I could add into my model to see if I can kind of control for it better. But you will still probably see a bit of heteroscedasticity in these models because the data is still clustered, right? So people are different shapes. If you've never looked at one of these before, what you want is kind of a very nice random uniform across the zeros here. All right. So there were little problems, I would say. There's a little bit of heteroscedasticity and a little bit of skew, but tons of data, probably the best guess. Now for effect sizes, we can use MU-MIN. So it's a simple R dot square GLMM. If you're using a logistic model, there's other functions. So this is the general model. So for linear models, it gives me R2M, which is for the fixed effects. I'm a little unhappy, right? So it says the fixed effects are less than 1% of the variance. That face. Okay, so my addition of this predictor is not super great. But the C here is sort of for the whole model, right? This is really where the random effects come in. So 42% of the variance, stop and think about that for a second. 42% of the variance, which is just crazy tunes, is due to people and the words. So much of priming research where it's like, well, sometimes we got this value and sometimes we got that value and we averaged over everything, guilty as charged. Might be simply because we're not super great at controlling for this very large amount of individual differences and differences in the words. So maybe I can find some predictors that will add to this and sort of shift that variance from being random to being known, like frequency. Word frequency is a very large predictor that I could add to the equation to kind of help deal with some of the other error in the model. So you would report both of those. So you would talk about models and fixed effects and random effects. One of my favorite things about rstats is this model parameters function because it makes these cute little tables. This is Markdown, so you can actually cut and paste it, But you can also pull this directly into something like Papaya if you're interested, and grab and have it print out in APA style. Okay, so just makes it nice and pretty for you. It shows you what and how to report those values. You can also standardize them. And so our standardized coefficient for our fixed effect is about 0.17. That's pretty normal. So this will be beta. Okay, do notice that the intercept is not 0 in a standardized model because of all the structure of the data. And then my new favorite thing, although I will tell you, you should edit this. But if you're brand new in this stuff, I get a lot of questions about like, what do I need to report? And I'm like, I don't know, everything. I mean, just stick all the numbers in there somewhere. There's a function in Easy Stats, the report package, that will give you an idea of where to start. Okay. And so if you say report model, it will tell you like, what are the things that you should include? Okay. It tells you, hey, talk about what the model is, talk what the effects are, and then here's an example of the intercept. And then the fixed effects, it kind of gives you them parameter by parameter. So it kind of gives you a good idea of like how to report these models. The problem for me is that it leaves out model effect size. So you should also talk about the overall effect size of both the fixed effects and the mixed effects. Okay. But it's a great starting point if you're feeling kind of like unsure about like what should I list, and here kind of gives you a good structure. Let me show you one more example. I think I've got time. Yeah, I'm good. Okay. I asked my husband 100 times how to spell diary, and every time it kept looking like dairy. So I think I have diary right, but proof that numbers and language sometimes don't always mix. Okay, I study language because I don't get it. I like numbers because they make sense, but the word diary in English, it's super weird. So our daily diary study, or it could be our daily dairy study, either way, is where it's from a student's thesis. His name is Jeff Pavlicek. We have published this data in a bunch of different ways because they're a lab that takes lots of data and then asks lots of questions of it. And is doing some cool, to promote Jeff for 2 seconds, doing some really cool work with veterans now, looking at, affect over time. And so in this particular study, we had them measuring a bunch of stuff, but the simplified version is they were given a survey once a day for like 2 weeks to measure their positive and negative affect and their stress. So these are students. We're trying to kind of figure out what we can do to make them like freak out less. Okay. Their research lab also studies the effects on mental health after natural disasters. So it's a really cool lab out of the University of Mississippi. Okay. So our example here, the dependent variable is stress, and our independent variable, our level 1, where each row of the data is sort of a different score, okay, is our centered PANAS scores. And sometimes when you do the models this way, they're called within. This confuses the heck out of me. So keep the names consistent. So it's a level 1 variable, but what it implies is it's within person. When you center them, essentially what you're saying is each score in the data set no longer represents a raw score of the data. It now represents a change score. So this is very common in clinical work. This is really the only place I ever see this, but again, I'm doing like cognitive psych and clinical psych with friends, so there's a lot of spaces in between. But they'll center the data so that each score represents a change. That's really useful here because we've got time. And so we could say that their stress is impacted by having more negative affect or less negative affect rather than a specific raw score of the affect. So it's a level 1 variable. And then we also added a level 2 variable, which is the average score across time. So for every time point, the participant's score is the same. Okay. So the structure of the data, which I'll show you in just a minute, we have their change score, which is at level 1. So that means that at each row of the data, it's a different score. And then their average score, and this is called between. When you get into interpreting this, essentially what you can say is, here's how much the change impacts the dependent variable. So within participant, how much does that change make a difference? Versus here's how much on average the score makes a difference. So if people start higher, maybe their overall stress is higher no matter what. But for people who have a lot of variability, their stress is varying in the same way. So it's like two different ways to examine. So like it's kind of thinking about the global effect of your average score. So where are you starting and how much does that impact your stress on negative affect? Versus like if I dig into the data, how much does each daily change affect your stress score? And that's a really cool way to analyze the data. And it's built from just having all of the raw scores. Our example many slides ago now was having these global variables, what school type it is, but here I don't even need that. I can kind of create it from the data. And our clustering variables in this experiment are participant and time. Because while we're interested in time, we didn't really want we were more kind of controlling for the fact that we measured it multiple times. So we wanted to kind of control it as a nuisance variable more than a measured fixed effect. So we weren't trying to see like, do they get more stressed over time or less stressed over time? We were just kind of like, time is a problem here. Let's control for it. But this certainly could change. I could be now interested in time. Do people have a random slope of time? The biggest problem is that these things are not linear at all. They tend to be cyclical. So we stuck time in there as like, this is a problem, get rid of it. All right, so here's our PANAS data. There's also some progress. This is progress towards goals. So we've got their PANAS score for each time point, their stress. I know it looks like it's the same, but this is their total number of stressors that they listed for each time point. And instead of treating time as time 1, time 2, time 3, time 4, if y'all have ever collected data from intro to psych participants, you'll know that they don't do things on time. So what we did was we actually calculated their distance from the start. So sometimes they would take the survey right when we sent them the text message. Other times they would take the survey, 6 hours later. So we actually treated time as a continuous variable. So evidence here that you don't necessarily have to have a categorical variable as a cluster. All right, so this data set, much smaller, but 113 participants across the entire data set that we got to take this study approximately 13 times with a little bit of variability. So some participants only had one data point. And so they're not super useful, but other participants had 15, but I don't have to drop any of them. So this is, again, where missing data would be very problematic for regular repeated measures kind of situation here. No big deal. Same steps. So I won't talk quite as long on them, so I can give us plenty of time to ask questions, but same basic idea. Let's interpret the results. Okay, so how stressed are college freshmen on average? And apparently it's 2 stressors. So in the what they did in the study was they listed stressors because they were actually interested in looking at the types of stressors and a different component to this. So they would list like, I have a biology exam, or my friends are being dumb, right? So they actually listed stressors. So they're whole numbers. So approximately 2 stressors, that's not too bad. I think what you do see in the data is as I got closer to finals, the numbers went up, but that's why time is a nuisance variable here, but about 2 stressors across time. Regular general least squares. Now let's add in our random intercept model here of just participant. Now I'm not using time as a random intercept because that, I mean, I guess it would make sense, like what's their average score? But I'm actually more interested in time as a random slope. So we'll keep just participants, because different participants will have different stressors, right? So some of them are more stressed out. Some of them are having too much partying, right? It's football season. Everybody's having a good time. They're not stressed yet. All right, so let's see. On average, okay, the standard deviation around our 1.5 stressors is 0.8. So some of them are not stressed at all. That's almost 0. And some of them are more stressed. That's almost 3. So we see there's a pretty good amount of stress, and considering the range of the data is not very large, right? It's 0 to, I don't even know what, 10 maybe. That's a pretty good amount. So just remember, my caveat to interpreting this number here is based on the range of the data. Right? So you can pull up the data and look at the average score. So how much of the intercept is varying. So on average, stress is about 1.5, but pretty good amount of range here, when the numbers can be 0, 1, 2, 3. And so it tells me I have 113 participants. Good, just a good double check, with 1,400 observations. You get about 10 to 12 for each person. Now our fixed effects, sorry, I don't know why it's highlighted. There we go. To get those fixed effects created, there are probably better ways to do this, but this is what we did, is we created average scores. So what is the mean score for each person? Okay, we use the aggregate function. There's probably a brilliant way to do this in dplyr, but I created an average score for each person. Okay. And the nice thing about aggregate versus something like tapply is it puts it in kind of a nice little data frame where it has the participant number, the thing I'm aggregating by, and then the score itself. So it makes it easy to merge it back into the data set. So then I merged it back in the data set before I learned the joys of left join and dplyr, but merge works just as well. So we're taking that score, their average score, and putting it back in the data. So we have a new column called negative mean. And then to create their centered score, because if you don't do that, this whole model will blow up. If you include the mean and the non-centered score, you will create a multicollinearity problem. So our centered score is their raw score minus their mean. And so now we have our level 1 effect of how much do they change from average across, in these different measurements, and our level 2 effect, which is how much is their average score. And that really allows us to take out 2 different questions. What about the change in their affect changes their stress? And what about the global affect changes their stress? So you can see why this might not make a whole lot, hopefully, a whole lot of sense for priming. Like I couldn't even think of the way to make it this level 1 and level 2. I was like trying to come up with something and it doesn't work. So the differences here are really based on like the research question. Okay? And so if you can think about the structure of the data, do you have different numbers for each one, or kind of a cluster of numbers? That'll help you keep level 1 and level 2 straight. The problem is sometimes people call this between and within as well. So it can be kind of confusing with the wording. So what's the answer, right? Fixed effects models, let's see. So here's our negative mean. Okay. So the mean score here is our level 2 effect. This is between participants. So for each 1 point increase in the PANAS, we see a 0.06 increase in stress. So on average, right, for every 1 point in our PANAS scores, which I don't remember the scale of this data, so maybe every 10 points in PANAS, we're getting a half a stressor. Okay. So in general, it's probably telling us that the stressors are probably about equal between people, but it is affected by their negative affect, okay, because it is less than 0.05. And how much does the daily change in PANAS affect their stressors? Also, about 0.07. Okay, but this is the change in score. So every 1 point increase in change from average. So what it tells me is it's both their overall negative affect, right? Their general, on average negative affect affects their number of stressors. So if you're more negative, you have more stressors. and the changes. So if you get more, if you're, 2 days from now, you're in a bad mood, you've had a long day, your biology exam was really hard, that change in negative affect also affects their stressors. So they're more likely to list stressors. And so what we think is this sort of like negativity bias, right? So you're more likely to miss more stressors if you're indicating more negativity. And so that's a really nice way to look at that difference. Like, which one is it? Is it the average score of negative affect that makes a difference, or is it the change in scores? And we've had studies where level 2 worked and level 1 didn't, and vice versa. And in this case, they both are important, right? So it's important how negative you are on average and how much your score is changing over time. Okay. Now, time's not in this model at all, but how much your score is changing in general, okay, from average. To add time to the model, though, to show you a random slope, okay, I've got real time in here. Okay. So for each participant, this is the thing we haven't seen yet, so it's new. For each participant, calculate a random slope. So here we've got just an intercept. So that's what this means, is just give me the intercept of participant is the way I think about the pipe. Here it's give me a random slope of time for each participant. So you'll have the random intercept because participant's still over here on the right side of the piping equation. I call this the pipe because that's what it's called in coding, computer coding, like Python and stuff, not like the R pipe. So it's just the one above the enter key on QWERTY keyboards. Okay. So each one, for each participant, give me a random slope of time. Because it might be that as we get closer to the end of the semester, finals, everybody's freaking out. So maybe they're getting more stressed over time. And what we're actually measuring is not the change in negative affect, we're measuring the change in life situation because we're getting close to the end of the semester. Okay. And so we're kind of wanting to say, okay, well, how much does the time matter? Now we have looked at this in a couple ways, and time is very, it is up, down, and left and right. So it's not linear. So potentially this should be a random, not linear slope, but here we just kind of were trying to control for it. All right, so what do I get? I get the standard deviation of intercept. Okay, notice that went way up. It was about 0.8. Now it's about 1.2. So by adding in the slope component, it moved more of it to the intercept. So now participants vary in their average number of stressors by about 1 point. We also get the effective time. So, if time, this is a little confusing because time is not actually a slope in this model at all, right? Like there's no time here, there's no fixed effective time. But what I'm essentially saying is if I control for the time, the variability between all of the different participants is 0.1. It's very tempting to think of these numbers as the actual like intercept because it's very close, right? It's 0.6. It's tempting to think, oh, the intercept is 1.3. Remember that this is the variability of participants' intercepts. And if I calculate the slope of time for each person, so how much are their stress score is going up and down across time, if I toss a linear line on top of that, the variability in that is 0.10. So it's not huge, but it's varying a little bit. And then you do actually get the correlation between the slope and the intercept, which is a whole nother problem that I have a lecture for if you're interested in understanding how to interpret those. From my structural equation modeling class, it's kind of hard to explain, but the negative component here means that as the intercept goes up, the slope goes down. Okay. So as they get more stressors, the slope becomes more closer to, well, I don't even know what the slope is, so it's hard to say, but this means that they're negatively correlated. So as the intercept value goes up, the slope for time goes down, and vice versa. All right. I don't ever see anybody report that. They normally just report these two standard deviations. Okay. Well, which model's best? Before we interpret it, which model's best? Because it could be that this random slope, especially because the variability is so close to 0, doesn't mean anything. So we've got our cool model here, but let's see. AIC, does it go down? Yes. Does it go down again by adding our fixed effects? Yes. Cool. Right? And it actually goes down one more time by adding the slope, the random slope. So I would say that my random slope model was the best model. And one thing I remember now when I was like, I lost my train of thought, how much does AIC need to go down to be important? And there's actually a big argument over this right now, but the general rule is 2 points. Okay, so as long as it's at least 2 points lower, you would consider that model better. I don't remember the citation, but I have it somewhere if you need it. All right, some quick checks. So this time it did actually, I could get it to run. Unfortunately, it's kind of small. Can I open image tab? Make this bad boy bigger? Yeah. So this will give you a good feel for a couple of different things. So this is actually very close to our plot that we had earlier for homoscedasticity. And you can see that, it's not great. But it's not terrible either. So you do tend to get these like flying spaceship, Star Wars ship shapes. So I would say this is a bit heteroscedastic. It also will kind of give you the linear fit line. So it does seem to be relatively linear. That's cool. Okay. It'll give you collinearity. And it says that both of these are low. Cool, I did it right. So I'm checking for multicollinearity, basically. Normality. So this is our QQ plot. See, I can tell it's pretty linear and pretty normal. Right? Pretty cool. So that check model function is really handy if it will not take 3 hours to run. You can also do check outliers, and there are a couple of different arguments. So you can do z-scores, Mahalanobis, and I think leverage. And here it tells me I don't have any, which is also cool. So just FYI, these are two really great functions for all kinds of models. How much of an effect do I have? Oh boy. Okay, so for our random coefficients, the variability of time and the variability of person, it's 53% of the data. Okay, so there's just a lot of variance in negative affect going on there. And some due to time. But for our fixed effects of the level 1 and level 2 predictors, we get about 8% of the variance, which in clinical psych was like, wow, what did we do wrong? Because that's amazing. So we got a pretty good effect size for just really one predictor. And then last, I can print out my cool chart. Now, I did not notice here that I did not run standardized effects, because in theory, it's a little weird here to run a standardized effect on a variable that's already been centered. A little strange. You can do it, but I think it makes sense to report these in raw score numbers because they've already kind of been manipulated a little bit. And so we can interpret those, and it shows you the cool way to put it in. Now, for some reason in this model, it actually gave me their version of effect size. I usually use MUMIN. This is just a different mathematical formula. That's why the numbers are pretty different. You could go with either one. I would just tell you to cite the one that you use so they know which equation, because they're just different forms of math. And this one, it's saying it's 70% almost. And that's what the little C stands for. I don't think I ever said that. I'm sorry. This is conditional. That means the random effects. And then M stands for model, which is the fixed effects. Oops, wrong way. Or marginal as well. Now you can also tell it to plot the model parameters. So if you have 5 or 6 different predictors, you can make a cute plot of all of the effects and their effect sizes, their confidence intervals. And then here now it just shows you how to report it. think that's all I want to say there. Yeah. Okay. So let me tell you about some other resources. I'm getting close to the end here. The free book on NLMs, which is Jess Flake and one other person, just jumped out of my head, is really amazing. And walks you through all this, shows you some of the equations without being too scary. Hopefully mine weren't too scary either. And it's kind of shows you how to do this in different formats. I think it's really great. It's all open source as well. There's a tutorial from Lisa DeBrine on how to simulate nested data. I was pretty sure I wasn't going to be able to get into Power today. That is a unfortunately tricky subject because sometimes it's hard to make up fake data that isn't too good. Like when I go to simulate these kind of models so I can calculate power, I often make up really good data sets and I have to find ways to make them more realistic. But Lisa has written a really amazing tutorial on how to do this. And the package is called faux, meaning the word means fake. And so it's a way to make up realistic data sets. So the whole package is great, but there's actually a very specific tutorial on random effect models that I think is really good. And every time I need to do it, I go back and look at it. And then if you're ever needing something to cite about why you should use a mixed effects model, I feel like this shouldn't be necessary anymore, but it is the very famous Gelman paper that talks about what multi-level models do versus don't. And if you like math, there's your math. There's way heavy on what, like structurally, what happens with those models. But I use it a lot as a citation, like the data's got a hierarchical structure, so I got a control for it. But in summary, right, so made it to the end here. What did you learn? Okay, so these models are flexible tools for structured and hierarchical data. And to me, it allows me to know a bit better where the error is coming from. Right? So is it, how much do participants actually vary? Sometimes the answer is 0, and that's really interesting. Okay? It doesn't improve your model any, but that is like, what? That happened to us on a paper. And I remember we had a kind of a fight over with the reviewers about, oh, take it out if it doesn't matter. And we were like, no, I don't want to do that. But we were able to report like this effect of the data, the structure of the data didn't matter, which was interesting. And it also gives you more power because you're analyzing every data point and not just an average of data points. And, sort of mathematically, I'm going back to the beginning where I said, what were your goals today, right? We're going to learn about what types of data is this good for, and a little bit about what is happening, inside the computer. It's basically regression with regression on top. Okay. So we've got the same basic regression equation, but for the intercept and or slope, depending on if you make it random or not, you're going to have more regressions because you have everybody's estimate rather than just one number. But the fixed effect component of it, if you use it as a fixed effect, is the average of all of those things. And now R, the last data point was, hey, can we learn how to run these? R does make these dangerously easy to run. And the easy stats makes this very easy to export. At least what should I be reporting? Now you still have to write it yourself, but you can get a kind of a nice structure for knowing what to report. So I think we've covered all the points, the main goals for today. And I wanted to say thank you for your time on a weekend to come and hang out with me and listen to me talk about how much I love multi-level models. And I would love to answer folks' questions. I'll hit stop at the moment, but I can always reshare if you have data or code questions. Thanks.
Thank you so much for that wonderful workshop, Dr. Buchanan. I really appreciate the detail that you provided on how to interpret all these coefficients and the examples that you gave. I think they helped really clarify these terminologies. So thank you so much for this amazing lecture. And I see some questions in the chat. There was one question asked towards the beginning. They wanted to know in the example of school and grade, which is the fixed effect.
School and grade. They're both fixed effects. So if you make the equation, I'll just retype it. So if you do learning, anytime you put, I think it was school and gender actually, right? So gender plus school type, right? Anytime you have something in the equation here, it's a fixed effect. And so that's why I'm just typing this as well, so it goes into the chat. But that's one thing I like about NLME is that you are forced to make the random ones a totally separate line so that you know that these are the fixed effects ones and these are the random effects ones. And sometimes they can be both. And sometimes they're only in one or the other. So hopefully that clarified. And then I think what we did in that particular equation was we made the school, so the random would have been something like, I'm writing it down, I think better in code, school number. Right? And so the school type was a fixed effect, but the school number was the random effect.
Okay, thanks for clarifying that. There was another question. Is it important to always exclude missing? I think they meant missing observations. What if I just run the model with the missing observation?
I think I excluded it in my data just out of habit. I think to make this whole lecture run smoother, but very practically, as long as you include that NA omit argument, it will exclude them for you. So you could leave them in the data set and just let it exclude. And I saw somebody said that the arguments for NLME and LME are different NA actions. So I always try to make mine explicit, but generally you just want to exclude them as part of the model.
Yeah. There was just one question came in just now. I have a question with the number of cluster and number of observations within a cluster. Are there requirements other than the power that we should consider when designing a study?
Great question. I will have to pull that back up for this one. So one thing you want to make sure is that they're never one. So I think that happened here, right? Right. So when kind of clustering the data, or the better picture here is to check the number of observations. So if you try to add a random intercept, especially, or a random slope where the number of data points within that cluster is 1, it will be unhappy with you. So that's really a big consideration. But then it also tends to affect the degrees of freedom. So this would be better in the second example. One second. But like it's affecting here what the degrees of freedom are. So it's the larger number of combinations. Let me look at the second one. Okay. So as the negative mean here, right, our level 2 variable, the degrees of freedom are smaller because those are clustered by person. And so that is how it affects power, is based on the random effect structure. So because I have a participant and it's a level 2 variable, you do have less power on that specific one because those scores are repeated. And that's one way also to kind of help yourself clarify which one's level 1, which one's level 2. Is anything with the smaller degrees of freedom is a level 2 variable. So it's tied to power, yes, but also just practical to answer your question.
Another question came in. Can we run MLM models with data coming from different sources? For example, dependent variable democracy index from varieties of democracy institution, but independent variable are mass level and from another resource.
Mhm. As long as they're combining the data in a way where the row still makes sense. So I'm helping a big team science project where they're actually doing something very similar to this, where they have the like raw data from the participants, and then they're merging in the country level democracy index, education scores, etc. And so those would be level 2 variables. And then we've got participants as our level 1 variable. So as long as it makes sense to combine them, I would say yes.
Um, okay, so this one is the last in the chat. Are there any R packages that allow you to top run MLMs without excluding the missing data?
Yes. I'm thinking. I think either way, you have to tell it what to do with the missing data. So let's say you have like 3 predictors and they're only missing one of the numbers, right? You have to tell it what to do with that number or it will drop the row. So you could use a package like mice, or it's a multiple imputation package to estimate that number. So I think in theory, they all let you run it, but they're going to make you do something with it. And then I see this last one too. Yeah. So is there a rule on the number of predictors? Oh, oof. Brains. No. You have to have more people or data points than predictors. So the level 2 variables might yeah, can your model run is actually a great question. Yeah, so the rule with regression is you have to have more data points than predictors because of degrees of freedom. That's the only rule restraint.
Yeah. So I think that was the last question. If my model does not run, which random predictors would you take out?
Yeah, we weren't able to get into convergence errors. So you will find that some models won't run. They will crash and you have to figure out why. And the convergence error is almost always 0 or 8, and it's not very helpful. So Kaya's question, I generally suggest starting with the simplest model. And so hopefully the model breaks at a specific point that you added something so that you would know that that was the predictor that caused it to break. And so I would take out the one that caused it to break. But if it's a random effect, the next thing I tend to do is investigate the number of data points within that effect. So that's why the first step I did was like, how many participants and how many data points do they have? And then the variance. So you can calculate the variance by cluster. So for each participant, tell me how much variance in the DV they have. And if you have a participant with 0 variance, that's generally a place that you can remove something because that will cause models to break when there is no variability within a cluster. Hopefully that made sense.
Yeah, yeah. So that was the last question, I think. Do and others have any more questions? If you do, you can. I think we still have time for some more questions?
I've got time. It was on my calendar till 12:30, so I wasn't sure. But I was trying to hit 2 hours so that people could run away and go have Sunday.
Okay, yeah, no worries. So I think we answered a lot of questions. Thank you so much for taking those questions. Um, and thank you so much, everyone, for taking time out on Sunday. Thank you so much, Dr. Buchanan, for agreeing to this and for this wonderful workshop. And we will be sending this recording to everybody. And we will also be sending all the resources and links, and also links to Dr. Buchanan's website. So you can check out all the other resources there as well. So, yeah, I think we can end the workshop now.
Perfect. Well, thank you, everyone. I appreciate it. Y'all's time as well.
Thank you. Thank you so much, everyone. I'll just end the workshop then. Bye.